Good morning. Here yet again for another session of CENG 3325 Structural Analysis. Today we are going to be looking at solving for deflection by integration. This is going to be the 13th lecture in the video series, and today again we're looking at deflection by double integration. And we're going to be looking at the simple case for beams. So deflection by integration. So let's consider deflection via integration. So the first topic here, what I want to do first is put together a derivation in terms of how we can actually get the equations of, so we can actually get the equations of deflection, building up from our equations of shear and bending moment. So previously we have looked at how to find the shear and bending moment in a beam by integrating the load function. But now I want to take this further and see that we can actually continue that 2 levels deeper and find both slope and deflection via integrating the moment function. So let's consider the geometry of elastic curves first. Of elastic curves, so let us see what happens when we have a small bit of length on a beam that is undergoing bending. So let's take a small bit of length of a beam and put it under bending. And so normally we would have a dx. If a beam is not under bending, we might just have a dx. But when we put it under bending, we would instead not just have a dx, but we would have an arc length, a ds. And so when we put it under bending, I'm going to be working on this derivation with a ds, which is an arc length. So I have an m here and an m here. Let's look at the geometry of a beam in bending. So I'm going to start by by sort of charting out a d theta. So let's say we have a beam, a piece of a beam, a differential element of a beam that is undergoing bending. And we have a d theta here. And here's our origin, the origin of the curvature. Then we have the beam itself, or again, this is really just a differential element of a beam, not really the entire beam itself. So for a tiny differential element, and I'm very much exaggerating the degree of curvature, if you have a beam, a steel beam or something, in your building, and it actually is bending like this much, I suggest you leave the building now, because someone didn't do their job. They obviously need to watch more YouTube videos. All right, so let's see here. All right, let's see here. And then I'm going to have my beam here under a bending moment m on either side. Bending moment m here on either side. And then I'm going to have my a distance y measured from the neutral axis of the beam here. Neutral axis, again, if you remember from mechanics materials, is the distance along the height of the beam where deformation is 0. Or where strain is 0, I should say. Then we're going to have another quantity, rho, which will be the radius of curvature. Rho is the radius of curvature. And of course, at neutral axis, so just kind of keep in mind, at neutral axis, stress and strain due to bending are 0. That's a blast from the past, recalling mechanics of materials. Stress and strain from bending are 0. R0. Then I can go ahead and label this as the neutral axis. So this is going to be my neutral axis. And here, my dx is equal to my ds. Dx is the same dx we looked at previously when you're doing integration or solving for shear moment by a method of integration. That is the actual length x along the beam. So in other words, you got to think about, one way to think about this is when your beam is undergoing bending at the neutral axis, because there's no strain there at that point, at that one location along the beam's height, the length of that arc length is exactly equal to the undeformed length of the beam, because there's no, or length of that section of the beam. Above the neutral axis, assuming positive bending, of course, above the neutral axis, your ds is less than your dx. Below the neutral axis, your dx, again, above the neutral axis, your dx is going to be, I should say greater than ds. And then below the neutral axis, dx is less than ds. So here, along this region, maybe I can actually label this. Here, let's see here. That's going to be in compression, so dx is greater than ds in this range, just to help us distinguish between length and arc length. And then this region, dx is less than ds. Dx is less than ds. Okay, so this is our coordinate system, our coordinate axes that we're going to be working with. Let's make sure you get that, and we'll be continuing on to look at normal strain on a fiber. Okay, so let us consider normal strain on any fiber. And it is important to keep in mind that we are assuming elastic behavior here. Any fiber. The moment this is not elastic, then this kind of goes out the window, and you have to make a lot of accommodations for that. Fiber, we're referring, of course, to fibers in a beam, or if you're of the British persuasion, you could spell that RE if you wish. Here, just a second. Oh. Did I zoom in too much? Oh, there we go. Normal strain in any fiber. So if we go back to our mechanics materials definition of strain, and you'll see this one again when you take steel and concrete. If you have your neutral axis here, here would be our neutral axis, and assuming positive bending, we would have a positive strain here, positive normal strain here, and a negative neutral strain or normal strain up here. And a positive strain down here, because this will be in tension, while the upper fibers will be in compression. So here, epsilon is equal to, now, epsilon will be equal to ds prime minus ds over ds. I should probably give you ds prime. Ds prime is the maximum arc length. Sorry, I just had to label something over here. ds prime is our maximum arc length. ds prime. So what this means is the strain at any fiber is going to be, we can determine it via a simple triangular ratio, and that's just going to be, well, this is the definition of strain. The definition of strain at any fiber is going to be equal to the difference between the length of that one fiber and the original fiber length divided by the length of the fiber. Then we can still work through a few other things. But one relationship that we can recall from basic geometry is the arc length angle relationship. So I know that arc length is equal to r times theta. Remember that in a circle? If you go way back to high school geometry class, if you have an r and a theta and an arc length s, remember this stuff? Wasn't that fun? Ooh, we could have you do a formal proof on the exam. That'd be, so much fun. No? Okay, fine. Contrapositives. So anyway, the relationship from geometry class we learned was that S is equal to R theta, where theta is in radians. So S is equal to R theta. So using the labels that we have here, we're not using a S, we're using a ds, and we're not using a theta, but a d theta. So ds is equal to rho d theta. We're not using an r, we're using a rho. So ds equals rho d theta. And then we can also say though that ds prime is equal to the increase in radius p plus negative y d theta. Again, where is this coming from? But if you looked on the previous diagram, you'll see that y is the distance upward. It's the distance from the neutral axis to the outermost fiber. And so the ds prime, the length of the outermost fiber, is just going to be minus negative y. Or that's our radius multiplied by the d theta. We'll get our ds prime. And then combining these together, if you throw all this together into one calculation, substituting like for like, etc., you can get that epsilon is equal to rho plus negative y d theta minus rho d theta over rho d theta. Again, just substituting ds in for ds and ds prime for ds prime. And then the d thetas cancel out, and you're left with epsilon is equal to negative y over rho. Epsilon is equal to negative y over rho. So at any point, the strain in the beam at any fiber is going to equal the negative deflection, is going to equal the negative y divided by the rho, divided by the radius of curvature. That's just really a basic geometry relationship.
And that y is where the fiber is located, not the total.
Yeah, that is where the fiber is located. Yes, that is where the fiber is located.
So just a question.
Yes.
In the previous class, we talked about I-beams, the W sections, as you call it. And the way they built it like that, you said it was to keep load away from the neutral.
Yes. Yes.
From what I'm hearing, or at least one thing you said was that at the neutral axis, stress and strain from bending is zero.
No, not at the neutral axis. Stress and strain from bending will be zero. Yes.
Yeah, so unless I'm making some kind of big error, why wouldn't we want?
Oh, okay. So the question, okay, it's a question on the nature of kind of a tangential question. That's fine. It was a question on the nature of I-shaped sections or W-shaped sections, or W sections, any I-shaped section. The question was, W-shaped sections are like mini bending shapes. They are the logic behind them is that we want as much area as far away from possible as the neutral axis, and we're trying to resolve that with the question is trying to resolve that with, well, if the stress and strain are zero at the neutral axis, why do you want to keep area away from that? Well, again, the whole idea is that no matter what shape you have, you're going to have a neutral axis somewhere, and you are going to have zero stress and strain at that neutral axis, assuming elastic. But the important thing to keep in mind is the design of I-shaped sections or W-shaped sections is that is the most efficient shape. It is more efficient to have most of your area far away from the neutral axis. I mean, I guess I don't know if I can explain that further. It's they're not really related. Yes, there's a neutral axis where stress and strain is zero. That's just any shape that you put into bending is going to have a neutral axis where the stress and strain are equal to zero if it's elastic. But beams just to perform more efficiently because that will give you the largest moment of inertia for the same amount of area. Does that kind of make sense?
Okay, I think I understand that last one.
Huh?
Okay, I think I understand what
Okay.
that was.
Okay. You know, ideally in terms of bending, if all we had to worry about was bending stress, if you were to design a beam that had, if you could design a beam that had the only thing that, if somehow magically the only thing you're going to put on it was bending, and you didn't care about dimensions at all, or constructability or anything else, theoretically, the ideal case would be almost a beam like separated by as large a distance as possible, and you would want this almost like a zero width plate, like a plate that's a tiny, 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 tiny fraction of a 32nd of an inch, and this would be like miles wide or something like that in terms of, now obviously as you learn in steel design there are many other failure modes and reasons why that wouldn't work, and also geometry wise it's hard to use a beam that has a flange a mile wide, but in terms of just the elastic equations, if you were naively looking at the theoretical limit of that, in terms of maximum bending efficiency, you would want a beam that's like infinitely tall and the flanges were infinitely thin and infinitely wide. That would be almost the ideal case for a bending stress. But of course, that's not, that's not real world, of course. Okay, so next I want to look at Hooke's law. The next piece we're going to look at is Hooke's law. Which we know for normal stress, assuming we're in the elastic region again, I keep coming back to that, but it is important. We can say that sigma, well, there's many ways to express Hooke's law, but one is that sigma is equal to epsilon times E. The normal stress is equal to the normal strain times the modulus of elasticity. So if I want to then go and express this in a function form, I can express this as sigma as a function of y is equal to E times epsilon as a function of y. So let me do some little side notes on here to explain what these are. This is going to be stress as a function of beam depth, or stress as a function of depth in beam. E, of course, is your modulus, the elastic modulus. And epsilon as a function of y, this is going to be your normal strain as a function of beam depth in beam. Or I can just say strain, it's pretty obvious, it's normal. Strain in beam, or strain as a function of depth in beam. Of depth in beam. In beam. Okay, so next I want to look at moment equilibrium about the neutral axis. I want to consider moment equilibrium about the neutral axis. Actually, I'll probably do that on the next slide. Moment equilibrium about the neutral axis. About the neutral axis. So let's look at the stresses here and then apply an equilibrium. So we have this. And the stresses. If I have my stress diagram here, with my neutral axis here. Actually, I'll probably should do that in a different color. Let me just show the stress first. That'd be negative compression and positive tension. So this would be stress in compression and stress in tension. And then we'd have an overall moment. Actually, let me show this. Let me show the neutral axis here. And then I'll have my moment here. basically what this is showing is that all of this stress must somehow come together to produce a single moment. When all of this combined across an area will produce my moment. And then some notation on labels and dimensions and signs. I have my depth y here, my depth location in a beam, my height at a fiber in a beam. And then I would also have something here that would be just my dsdA, or my little SDA, my differential element. So if I integrated this across the area, I would get my moment. So my moment is equal then to the negative integral. Moment is equal to the negative integral. The negative comes from the fact that for equilibrium, these have to be equal and opposite. That the moment would be the moment applied to the beam. The negative here, let's see, negative area integral of here, negative area integral of sigma y, or sigma as a function of y, not yield sigma, not yield stress. Sigma function as a function of y dA times y. So basically, integrating the stress over the area will give us the moment, because this is basically integrating stress as a function of area. This is a force, and our y here, this is the distance from the neutral axis. So integrating the two will give us our moment, and this is our sigma as a function of y distribution. This is our sigma as a function of y distribution. So we now have an expression for moment in terms of stress and area. And let us look at next at applying Hooke's law to this. So let's apply Hooke's law. And Hooke's law, of course, is that, well, there are many expressions of Hooke's law, but one that we can look at is that epsilon as a function of y is equal to negative y over rho. Negative y over rho, which means that then we can pull out our, or then we can put this into our moment expression from before. And we will get that m is equal to the negative area integral of E times epsilon as a function of y times epsilon as a function of y times y dA. And this is then equal to the area integral of E y squared over rho. E y squared over rho dA. And we can apply a couple other bits of information. As we've seen previously, we know that dx is equal to rho d theta, which then leads to solving for rho. Rho is equal to dx d theta. Dx over d theta, or in turn, 1 over rho is equal to d theta over dx. D theta dx. So, next I want to look at this integral here. I want to replace the rho with d theta dx. I know that 1 over rho equals d theta dx, so I'm going to put that in here. And so the area integral then, so m again is equal to the area integral of E times y squared d theta dx dA. Now, this is an area integral. We always need to remember that. This is an area integral. Or in other words, this is an integral across the surface area of the beam. And a few of these things aren't going to change. One of these is E, and one of these is d theta dx, as you integrate across the area. So what can we do with them in terms of integration? We can pull them out of the integral. Yes, exactly. We can pull them out because they don't change over the cross-sectional area. They change, well, E is going to be constant for a beam of a given material, and d theta dx will change along the length of the beam, but d theta dx will not change as you integrate across the area. And that will give you E times d theta dx times the integral of y squared dA. Does this look familiar? Should, hopefully. If you remember your statics or mechanics of materials. The integral of y squared dA. This is actually something you should be very familiar with, hopefully. This is your moment of inertia I. The area integral of y squared is the moment of inertia of a cross-section. So we can then say that moment is equal to EI d theta dx. And this d theta dx is also equal to 1 over rho. Also equal to 1 over rho. So M equals EI d theta dx. Now, I would like to then, I'd like to rework this and apply an integral. So we now have something that we have a relation of theta and x and the moment applied related by our EI, related by our cross-section property and our material property, relevant material property. So then I can say that d theta dx is equal to m over EI, which equals 1 over rho. 1 over rho. And this is often referred to as the curvature of the beam. So this here is the curvature at a point. In other words, we refer to 1 over rho as the curvature. One over rho as the curvature. And so I'm going to use this part here, though, for my further derivation. And I'm going to separate the variables. Let's separate the variables. So I can do if I move let's move the d theta over here and say that we have d theta equals m over EI dx. And then if we integrate this, if we integrate both sides, what will we get? We will get the theta as a function of x is equal to the integral of m as a function of x over EI dx. Over EI dx. And so then this is going to be one of our main equations, or one of our key main equations. And what this tells us is this is the slope as a function of x. Slope of beam as a function of x. Now, what I'd really like to do, though, is relate deflection to curvature. Let's relate deflection to curvature. So I went and read through a calculus textbook, and I found this equation here. I found that 1 over rho is equal to relate the deflection to curvature from a calculus textbook. I found that d squared y, or the second derivative of y with respect to x, 1 over rho is equal to this over 1 plus the second derivative again, or the square of the first derivative. dy dx quantity squared, and this squared. Now, this is fine and well, but This is not necessarily what we want to work with because, well, the problem with this, first the problem with this is I'm missing a 1. That's one problem with it. But the main problem with this is that this is difficult. Well, not that we as engineers are concerned with working with difficult math. It's more just that we want to make things more streamlined. And so here, let's think about this. We know that if you think of this mathematically, if you multiply or divide by a very small number, is that significant? Yes, it is. If you have 10 and multiply by 0.0001, that is significant. If you divide 10 by 0.00001, that is also significant. What if you add or subtract by a very small number? No, it's not. That's not significant. We often make this assumption in engineering, even in some sciences, and that is that we neglect very small things. So we're going to assume small deflection, and not just small deflection, but small deflection squared. We assume that a small deflection squared is approximately equal to 0. We're assuming small deflection in the first place, and we take something that's already very small and you square it, we're just going to assume that's about equal to 0. So this will then collapse to the relationship that 1 over rho is equal to d squared y over dx squared, or the second derivative of y with respect to x. And so then, what I can do next is, again, this came from calculus, but what I can then do is put in my relationship m over ei, replace 1 over rho with that. M over ei equals the second derivative of y with respect to x. Then separating the variables, I'm going to put the dx here. Let's do the integral of m of x over ei dx equals dy dx equals theta of x. Equals theta of x. Or if I double integrate this, if I bring the dx again over here, so basically I now have I have dy dx equals the integral of the moment over ei. Then if I bring this back over here and I separate the variables again, I can get the double integral of m as a function of x over ei dx dx, the double integral, dx dx equals y as a function of x. And that's what we've really been working our way up towards. Because what we have here is we know that if we do the double integral of m as a function of x with respect to x and baking in our ei, we will get a function for the deflection as a function of x. So I might come back and just rewrite this for emphasis here. Our final equation that we've been working through on this derivation is that y as a function of x is equal to the, and let me go ahead and pull the 1 over ei out. We often do that. 1 over ei times the double integral of m as a function of x dx dx. And now we have something that we can solve for deflection via integration. And this equation is baked into the heart of basically every structural engineering or structural analysis package out there, software package out there. So let's review assumptions. As we review the assumptions baked into this, 1, straight beams. If your beam is at a curve, that's going to cause some issues, and you'd have to redo their derivation. 2, transverse loads. 3, Hooke's law is applicable. In other words, we're assuming that we're in the elastic section of the material's behavior. We assume that plane sections remain plane, very common assumption. And also we assumed small angles and deflections. Small angles and deflections. All right, so now we know now we have equations for both the curvature and the deflection of a beam as a function of x, and we can then apply them in the next section. So that'll do it for today. If you have any questions, feel free to contact me. That'll do it. Thank you for watching, and as always, thank you.